my great pleasure to introduce Mark Berman here from CSIRO. I bet you know Mark for almost 2 decades now, right? Anyway, time flies. Yeah, so Mark has been involved in geospatial imaging and especially hyperspectral imaging for many years. He also has done a lot of work in the area of morphological imaging, and he's now a chief research scientist at CSIRO. CSIRO is the largest research institute in Australia. And for the past, I guess, couple of months, he's been at Stanford, or maybe more than a couple of months.
No.
At Stanford for
5.5 weeks.
Sort of a summer teaching position. And so today he's going to talk to us about spectroscopy and hyperspectral imaging. Mark?
Thank you, Luke, and thank you for having me here. Okay. This will talk about some of the work that we've been doing over a number of years in these areas. I'm with the division of CSIRO, which I'll talk about briefly in a minute, called Mathematical and Information Sciences, or CMIS for short. At the bottom, you can see a number of collaborators over the years, mostly in my home division, but also 2 key collaborators in another division called Exploration and Mining. Okay, here's an outline of the talk. What is CSIRO? I'll tell you in a minute. What are spectroscopy and hyperspectral imaging and why are they useful? And major areas of our hyperspectral research, it's all about mixture models and what's called unmixing. And they're 2 extreme cases where you have a spectral library, what's called a spectral library, and I show some applications in mineral exploration, talk about what we've done so far and some future work. And then mixture models where you don't have a spectral library, and I'll give a very brief application in biotechnology just to illustrate the point in a low dimensional setting. And then I'll give an example in remote sensing, which probably of more interest in broad sense to people here. I'll talk about some recent extensions of our work by others, and I'll talk about some future work. And please ask questions as I go, but not too many. I gave a similar talk a couple of years ago, and I had so many questions I only got halfway through. So they invited me to come back the following week to complete the talk. So I've got, what, about 45 minutes? Sure. Okay, thanks. Okay, what is CSIRO? It actually stands for Commonwealth Scientific and Industrial Research Organisation. It's a little over 80 years old. It's Australia's largest research organisation. It undertakes research in a whole lot of scientific areas: agriculture, environment, health, information and communications technology, advanced materials and manufacturing, minerals and energy, transport and infrastructure services, and astronomy. It's got an annual budget of about $1 billion US. 70% of that comes from the Australian government, and the other 30% of funding comes from industrial work. So its focus is very much on customers' needs. There are about 6,500 staff at over 50 sites in Australia and overseas. So I guess we're comparable in size to Google, but we're more... Well, no, you're spread out as well, aren't you?
Much bigger.
Sorry?
We're much bigger than that.
Okay. Now, can I ask, how many people know anything about spectroscopy here? Oh, so there are a few of you know. Okay. But obviously not all of you. There are actually many different types of spectroscopy. Typically, the amount of light that an object reflects, absorbs, transmits, scatters, or fluoresces is measured at many wavelengths, often but not always equally spaced. We'll mostly be concerned with reflectance or absorption spectra. And to make life easy, absorption is just minus log of reflectance. I'm used to, in remote sensing and the mining industry, they used to work with reflectance. And you'll see spectra, these curves with the features pointing down. In the life sciences, they used to work with absorption. And because of the minus sign in their game, the features point up. Okay? The log obviously has a difference too, but the main effect is the minus sign. They can often be represented as a smooth, low-frequency curve with absorption features which are intermediate frequency. And of course, the noise is the high frequency. The spectrum of a material tells us about its chemistry, so some examples follow. Okay. These are taken with a spectrometer called an ASD, which gives you a measurement at every nanometer from 350 to 2500 nanometers. But I'm just going to show you spectra between 400 and about 1300. Okay? And to give you a frame, this is called the visible and near infrared. To give you a frame of reference, blue light is roughly between 400 and 500 nanometers, green is between 500 and 600, and red is between 600 and 700. So if I take some samples of green vegetation, now these are not repeat samples, they're actually different leaves or or, well, I guess mainly leaves, okay? And so what you see, you can see that there is a peak between 5 and 600 in the green, which is higher than the blue and the red, which is why our eyes recognise the green, because it reflects more green light. But if you go into the infrared, you can see it actually reflects more light in the infrared, but our eyes can't detect it. And a lot of these actually have, because they're green, they have water, and these features here are due to water. Okay? On the other hand, if you take dry vegetation, which is typically red or yellow or brown, it actually reflects more between 6 and 700 than in the green part, 5 and 600, because that's the colour we see. But you go in the infrared and the water features have disappeared because it's dry. Okay, so in a very simple way, I'm showing you what spectroscopy is measuring at a very coarse level. These are spectra of a mineral called hematite. Does anybody here know what hematite is? Yes? Yes, but the main thing is it's an important iron mineral, right? There's several, hematite and goethite are the main minerals, iron-rich minerals. Okay, and you know what colour it is? Well, it's reddish. Okay, goethite's yellowish, so it reflects more light in between 6 and 700 than in the green and the blue parts, and then it has a bump and goes up and then down, then up like that. Lazurite is a mineral that's known in the jewellery trade as lapis lazuli. Okay, does anybody know what lapis lazuli looks like? Blue, that's right. So it has a peak in the blue and then goes down and then goes up. Now my wife actually has a fake lazurite. It's called a sodalite. It looks just the same here, but if you move in the infrared, you can actually tell the difference between lazurite and sodalite. When I told my wife a few years ago, she said we should start a business using spectroscopy to identify fake jewellery. Okay, so actually let's move into what's called the shortwave infrared. This is with an older spectrometer called a PIMA, which is where I started in the 90s with collaborators. It measures between 1300 and 2500 nanometres at 2 nanometre intervals. It's the size of a shoebox. It was made for geologists to take out in the field and make point measurements of spectra. Okay, and these minerals are, in mineral exploration, you don't look for gold or silver or zinc or copper directly. You look for other minerals called alteration minerals, which are sort of signposts. I won't go into the details. An important class of alteration minerals are called white micas. When we started in the 90s, we just had two, illite and muscovite. And you'll notice all of these white micas have a feature, an absorption feature around 1400, another absorption feature around 2200. And you can see the background shape, the low frequency bit varies a little. I'll explain why in a minute. But really, when a spectral geologist looks at these, he looks at where these absorption features are in their shapes. And the way you normally tell the difference between illite and muscovite is by this feature here, which is due to water again, but it's bound. Okay, so I've seen them take a muscovite, wet it, measure its spectrum, and it looks like this, essentially. And then they put it in the microwave for a few minutes to drive out most of the water, and it looks like this. With an illite, essentially you can't drive it out. You can if you go to about 300 degrees Celsius. So it's called bound water, and that's the main way you distinguish between these. And then more recently, we subdivided muscovite into muscovite, pragonite, and phengite. Whoops, as we understood, or as my colleagues, geological colleagues, understood the differences. Basically, with muscovite, the feature's around 2200, okay? With pragonite, it's around 2190, and with phengite, it's around 2220. And basically, that slight shift in the position of the feature is indicating substitutions between potassium, sodium, and either iron or magnesium. So you can tell just by subtle changes in position and sometimes in shape, you can actually detect substitutions. If I showed you the formulae for these things, they're quite complex, okay? And they're geological names rather than chemical names. So for instance, geology started in many ways before chemistry, and the names just don't reflect the chemistry. So for instance, can anybody tell me where the name muscovite comes from? Moscow. Yeah, it was discovered near Moscow. And there are lots of minerals named after the people who actually discovered them. Okay, so that's part of the problem that we have to deal with. Okay, so a number of things to notice. As we move into shortwave infrared, the features of importance have a higher frequency. what I call intermediate frequency. The backgrounds vary in shape. They have very little information content. And you also have variation in brightness, okay? That's either natural. You look at 2 leaves from a tree. Some are slightly darker than others, okay? Or there is a lighting issue. If you have the sun, okay, and you've got trees facing the sun, you're on the side of a hill, trees facing the sun will be brighter, and those on the other side will be darker. So there are all those sorts of variations. And this, to first order, they're essentially multiplicative. Okay. Most of what I've said is on this slide. There are brightness variations due either natural variation or variable illumination. They're predominantly multiplicative. Most of the information is due to spectral shape. There's a whole issue about scaling the spectrum, which I won't talk about here. That's something I've been talking to my students about. The absorption features are usually higher frequency in the shortwave infrared than in the visible and near infrared. And the backgrounds are due to either scattering or the presence of other minerals such as quartz and feldspar, which have a very low frequency signature in that part of the spectrum. But these minerals actually have a distinctive spectrum higher up in what's called the thermal infrared. And I've been doing some work there lately, and we'll be doing more as time goes on. Traditionally, the backgrounds are removed before subsequent analyses, such as taking the convex hull and taking the upper bit of the convex hull and either subtracting or ratioing. Okay, so what's a hyperspectral image? A hyperspectral image produces a spectrum, typically tens or hundreds of numbers at each pixel. So hyperspectral images enable us to map variations in chemistry. In fact, in the chemicals industry, it's called chemical imaging. The original hyperspectral sensors, I'll show you one later on, the data from one later on, in the 80s and 90s were airborne. They were used mainly for exploration, environmental and military applications. There are several hyperspectral satellites due for launch over the next 6 years, starting this year, by a number of different countries. The US is probably go up to about 2013 or 2014. There are now hyperspectral microscopes and cameras being used for terrestrial applications, such as medical diagnosis, burns analysis, skin cancer, biosecurity, pharmaceuticals, forensics, agribusiness, exploration and mining. So it's a whole burgeoning field. Okay, let me show you one example, which unfortunately I won't have time to come back to. This is an example of part of an Excedrin tablet, well known in this country. It's a company on the outskirts of Washington, DC called Spectral Dimensions that makes its living just by doing hyperspectral, developing devices and software for doing hyperspectral imaging of tablets, okay, for tablet inspection. Okay. This is in the range 1200 to 2400, which is more or less the same range as the PMS spectrometer, which is 1300 to 2500. But instead of being 2 nanometers apart, it's at 10 nanometer intervals, okay? And it produced 121 images. Unfortunately, that's 11 squared, so I can show the data in a grid. These are some sample spectra. Because it's in the life sciences, the features point up because they're absorption spectra rather than reflectance spectra, okay? With techniques I'm going to talk to you about later, but I won't have time to show you, we can actually take those 121 images and decompose them into maps. There are essentially four ingredients in there, right? Caffeine, aspirin, acetaminophen, and filler. And you can average, those are the concentrations or proportions, maps of each of those constituents. And you can average those proportions and get an overall estimate of what's in there. And that's actually pretty close to what's on the bottle, on the label on the bottle from which this tablet came. And note it's only part of a tablet and it's only looking at the surface. It's within a few percent of what's advertised on the bottle. But it's also important, once you've got this map, you can actually, well, you can visualize, but you can also test for the spatial distribution of the ingredients. Because if it's not, it's important it's uniformly distributed. If you have, as you know, Excedrins for migraine headaches. If you have a 5-year-old child who has a migraine and you take that child to the doctor and the doctor says, give the child half a tablet. If it's not uniformly distributed, the chances the child may get too much or too little of the active ingredients. Okay, so what are major areas of our hyperspectral research? In many applications, most pixels contain a mixture of materials. Where I started with this was in remote sensing. Airborne instruments, depending on which instrument it is or how high they fly, they might be 30 meters by 30, a pixel might be 30 meters by 30 meters. My office, which is a fairly standard size office, is 3 meters by 3 meters. So a typical pixel is about 100 times the size of a standard office. The chance of that pixel containing one material are actually very small. And perhaps surprising at first, but not surprising on reflection, in a microscope, the same is true. You know, you just look in finer scale, you see more. Okay? So our research has been focused on what's called unmixing spectra into their constituent materials. The older stuff, which is first developed in the 90s but still going on, fast and reliable identification of material mixtures with a spectral library, and that's called the Spectral Assistant. More recent work is fast and reliable identification of material mixtures without a spectral library. In in the hyperspectral literature, that's called the Endmember problem. So this algorithm was originally called iterated constrained Endmembers, and the guy who actually programmed it up said, well, this is too much, I'll just take the initials and call it ICE.
What is the spectral library?
I'll come to that. Okay. So the Spectral Assistant is about the identification of material mixtures with a spectral library. It's been developed since the mid-90s. So a spectral library consists of spectra of pure materials, okay, or notionally pure materials. And then you have a simple model, which I'll show you. And from that model, if you have a mixture, you unmix into the constituent components, okay? So the Spectral Assistant identifies pure minerals and mixes of 2 or more minerals from a spectral library. We're now up to version 6, but that's not been publicly released. Version 5 has 2 libraries of pure materials. The larger library and the more important one is the shortwave infrared library. It has 299 wavelengths. It has 55 materials, soon to go up to over 60, with various minerals, dry vegetation, wood, Teflon, plastics. I'll show you shortly. A newer, less developed library is in the visible and near infrared, which has 163 wavelengths and only 17 materials for iron ores such as hematite and sulfides and green vegetation. This is what we started with for the developing the shortwave infrared with this PEMA. As I said, it's about the size of a shoebox. Building libraries is a very time-consuming business, okay? And, well, in this application, certainly. My main collaborator, John Huntington, took a PEMA, went around the world, went to the US Geological Survey, went to various mining museums, took samples that were notionally mineral A and measured their spectra. And it turns out that some of these things aren't mineral A. There may be mineral B, which is similar but not quite. It's got a substitution, basically. Okay, it's not quite the same. Or sometimes there's a little impurity in there, you know. The geologist has actually looked at it. They haven't done a full chemical analysis, and they put it in the collection, said this is such and such. And it and that affects, if you've got impurities in there, that affects things. So there's a whole slow process of culling. Okay, and in biology, it's even harder. If you think at the microscopic level, how do you actually get pure samples of things in a cell? It ain't easy. Okay, so this is the basic model. There are 3 main components. Okay, let me just focus on here. There's a thing called Beer's law, which says in this very intimate situation, to first order mixing is multiplicative, but it really doesn't make very much difference whether you take logarithms or not. Well, when you take logarithms to make things additive. Okay, this is the main model. You have 2 sums, and I'll talk about each sum separately. Okay, M is the number of materials in the mixture. EJ is the mean spectrum of the Jth library class out of M. And of course, and these are the weights. Now, if you're taking, the simple way to think about it, here you've got a pixel, on here, this side you've got material A, that side you've got material B, right? If it's 40% of material A, 40% of the area is covered by material A, 60% is covered by material B, then sort of the naive sort of model says that the spectrum I'm looking at is 0.4 of the spectrum of material A plus 0.6 of the spectrum of material B. But you've got a brightness variation, so you constrain those weights to be non-negative, but you don't constrain them to sum to 1, okay? So that's, the constraint is that these weights are non-negative. And we model the background as a low-frequency cubic spline, okay? For those of you who know about cubic splines, we just have 2 knots, which can be modelled as a sum of 6 basis functions, plus we always put in water. Water is ubiquitous. In spite of a drought, it's ubiquitous, okay? And people actually mostly aren't interested in the amount of water, so we always fit it, okay? But unlike these alphas, these betas are unconstrained, okay? And then we have an error. My background's in statistics. I tend to think about statistical models. And the implicit assumption is that there is a common within a common covariance matrix. That's actually incorrect, okay? But it's really difficult to, if you assume different classes, if, you know, here we have 299 wavelengths, so we have a 299 by 299 covariance matrix. We just don't have enough data to estimate it for each separate class, so we have to lump them all together.
Question, when you say background, does that mean basically the sun radiation?
No, I'm talking about the low frequency. Remember, there's low frequency variation, which doesn't tell you very much about what's in the spectrum. That's how we're modelling it. We're modelling it with a low frequency spline.
Well, what is that?
Yeah.
What do you mean, what is it?
Where'd those photons come from?
Well, I told you that they're due to two main most likely sources here. Either there are other minerals in there, such as quartz or feldspar, which have a low frequency signature in the range we're talking about, or sometimes you get these things, these changes due to scattering. I haven't got the example here. I'm not going to show the example with the tablet, but if you ultimately you can see by there's some diagnostics that will show you that there's some particles in the tablet that actually are facing slightly different way, and they scatter the light differently, and the light actually has its main effect in the low frequency. Okay, so it's sort of it's variation that you're not interested in, and you've got to model it out. Okay.
So it's basically typically something non-mineral,
Well, no, quartz is a mineral. Feldspar is a mineral.
something grey or brown that's just merged with it. Is that essentially?
No, it's one of two things. It's either minerals that have a low frequency information in the shortwave infrared, or it's due to scattering. Okay. Unfortunately, I don't have the time to show you everything, and I'm happy to talk to you more about it offline. But that's what it is. It's this extraneous stuff here, right? You can see the variation, right, in the low frequency, which doesn't tell you very much. Okay. We're trying to model that out, and things fit better if you fit everything simultaneously rather than one by one. Okay, so that's how that model is. Okay, the second part is we go into, some of you will have heard of linear discriminant analysis. You can do this in a subspace called canonical variate space. We do have a penalised version of this, okay, because we don't have enough data to reliably estimate the within-class covariance matrix. It's a paper a little over a decade ago by some people I'm working with in Stanford where they have a way of penalising this. And we do that for two reasons. One, for dimension reduction, okay? And secondly, for decorrelating the data. So effectively, then you can use least squares type approaches rather than working with a Mahalanobis distance, okay? And the other thing is fast subset selection procedures. We have a library of 55 minerals or materials, one of which is water that we always fit. So there's another 54. In any particular mixture, you're unlikely to find more than a few. You're not, it's silly to fit all 54. You're going to overfit, okay? So you actually want to find small subsets and then make a decision about which is the right number. So for the shortwave infrared library, you have to look at, if just at mixtures of two, you have to look at 54 choose 2, which is 1,431 possible mixtures of two materials, okay? And so we have fast subset selection procedures for doing this. Because the model is wrong, you can't use F-tests or, information theoretic things like Kaike's information criterion or minimum description length. It doesn't work, okay? We had early on with the pure data, most of them had actually been chemically analysed, and we had maybe a few dozen samples of mixtures of 2 and maybe half a dozen of mixtures of 3. We just didn't have enough to work out, for mixtures of 2, we empirically worked out a rough rule of deciding whether it's 1 or 2. We're now trying to do 3 and 4 because we're seeing examples of that. Now, this software has been incorporated into another CSIRO package called the Spectral Geologist, which I'll show you briefly shortly, which is sold commercially, and it's been sold to over 100 exploration and mining companies, which in that game is pretty good. And it can analyse tens of thousands of spectra in a few seconds. Okay, let me show you a quick example. Here, I've showed you these before. These are white micas. The key to note is that they all have these absorption features around 1400 and 2200. This is another important class called candites, okay, and there are 4 in that class as well. The important thing to note is they have a doublet around 1400 and around 2200, and the doublets are all slightly differently shaped. Okay. There is one of the early samples I worked on. When you look at it, it looks like, you know, it's got this single feature, it's got another single feature here, and it's got this water feature, so it's probably illite. But if you look, there's a little bump there on the shoulder. And when I showed it to my collaborator, John Huntington, who's an expert spectral geologist, he said, oh, it's probably got a bit of kaolinite in it, okay, because of that doublet. So you can remove the background parametrically, okay? And what I'm showing you here, the black curve is the background corrected true curve, and then the red, green, and blue are the best 3 fits of a single mineral, okay? And you see the black, none of them can quite get that shoulder. But if you take a mixture of two, and these are the best 3 mixes of 2, and they're all a candite plus a white mica, they can all get that shoulder. And you've got a score called the standardized residual sum of squares, and it's gone from 228 to 55, which is a highly significant change. You know, our threshold is 1 point, for the ratio is 1.3. Okay, so it's a very significant thing. But one of the questions that we're grappling with is how confident are we that, say, the best mixture of 2 minerals is the correct answer? Posterior probabilities will be useful, but what are appropriate priors? Okay, so where have we gone with this? Well, my collaborators are geologists, but they also have a group of engineers who build things, okay? And they've built a thing called a high logger. They've actually now built several of these, and now the Australian government is funding them to build 8. There'll be 1 in each of the 6 Australian states, plus 1 in the Northern Territory, so mining companies can go to a central location. Because up till now, they've been actually taken to mine sites, and it's quite a business. And they'll have 1 of their own. And basically, it's a spectrometer mounted on top of a stage, and you take these trays of core that go on the tray, and the spectrometer moves, or sorry, the stage moves up and down, and the spectrometer quite quickly measures a lot of spectra. Now, this is important. You may know Australia is a major exporter of minerals, but most of the large deposits, or maybe all the large deposits we know of that are near the Earth's surface in Australia, have been discovered, okay? And China is buying some of these, particularly iron, at an incredible rate, so our deposits are going down quite quickly, of iron ore in particular. So there's a campaign on to look further beneath the Earth's surface, several hundred metres. It's a flagship in CSIRO called Minerals Down Under, which is funding part of my time. So this is a screen for the spectral geologist. What I'm actually going to do is just bring it up. Put this down so I can show you a little bit better. This is with a smaller data set with about 18,000 spectra. Okay, that's actually run, as you've watched, it's actually run the Spectral Assistant as it comes on. Okay, there's other things in here. So what do we see? I'll put up another few things here. Oops, it's a floater screen. Okay, so what they do, they take all these trays, and from that one site there are dozens of trays, and they reconstruct it into a virtual. The geologists actually like to see the rocks by eye because they can interpret a lot by eye. Okay, so we do this, but you can actually home in. So I'm focused now on this spot here, right, which is blown up. The pixel is that wide and maybe this long. And you can see there are greys and there are whites and there are browns in there. So there are a number of different things in there. Okay, and you can also, oops. Blow this up. Okay, so what do we have here? This is just a number. This is a sort of a colour coding of the spectrum. And this here is in the shortwave infrared, identifying what the spectral assistant thinks is the composition. So if there's only 1, it says, I think there's only 1, and this is here in the illite. If it's 2, I think then it gives the 2 and says it's a mixture here of siderite, muscovite. This is the measure of the error, and then it similarly does in the visible and near infrared, but there's really little going on there that's spectrally, what we call spectrally active. Okay, and you can see here, for instance, this pixel 1009, it says a mixture of halloysite and ancrite, but in fact, I don't know if you can see this, but it's actually now saying it's a mixture of 3, and it's actually not a mixture of 3, it's a mixture of 4. So it's missed that little feature, which if you go, so it says auto, it's made this decision, but if you want to override it and say what's mixtures of 4, it finds a chlorite. I haven't got my glasses on. But so You can see part of the problem. We're actually seeing now things which are mixes of 4, and we want an automated and reliable way of being able to estimate it. Okay, so there is a typical drill hole consisting of 67 drill trays. I didn't bring that one with me, unfortunately. And it's got about 60,000 spectra, and it actually measures about 500 wavelengths between 400 and 2500. It's about 30 million numbers, which is probably, well, not probably, certainly small by your standards, but still fairly large. But at each site, there are about 100 drill holes. So there's a lot of data to analyse, and then the geologists take this and they have these 3D models of what's happening. Okay, and then of course you can summarise that information. So that's the summary for these 3 white micas down a drill hole and some 3 minerals called chlorite. Now, talking about the perversity of geological names, chlorite contains no chlorine whatsoever. Okay, but the thing I want you to focus on here is it's mostly blue here, which is illite, mostly green here, which is muscovite, and mostly red here, which is fengite. So there's a gradual change going on from something that's got more sodium, illite, then it's got sodium and then there's substitution of iron and magnesium in there. And you'll see it's a bit noisy because these are probably mixtures. I suspect a lot of these greens should be blues. So there's spatial information that you can use. So I'm just going to briefly talk about current and planned developments, one of which is incorporating spatial context. The gross classification trends on the previous slide are probably correct. The individual classifications are noisy. Should be able to improve the classifications by using a hidden Markov model. There's a large number of states, say there are 54 materials, but it's actually grown since then. So you've got 1,431 mixes of 2 materials, plus the 54 pure ones. So you've got a 1485 by 1485 transition matrix, and larger with mixtures of 3 or 4 minerals. So you also need to estimate the mixing proportions. There's a computational challenge there which we have yet to address. Another issue which is quite important, which is part of the reason I think we have difficulty, we get things right about 85 or 90% of the time. And when we started, people said that would be good enough. And now the customers say, well, I can see these ones are wrong by eye. So now we've got to get it close to 100%. So we're thinking about ways of doing that. But here what I've taken is the standardized residual sum of squares of the training samples under a theoretical model where they all have the same covariance matrix. The expected value is 100. Okay? And here I've taken the individual ones and take the mean within each class. And you can see there's some classes which are very highly clustered, more so than others, which is indicative that there are different within class covariance matrices. So I actually wanted to look at how to incorporate that with the fact we don't have much data, which is an interesting challenge, because that will give us improved estimation of the number of components in the mixture. We'd like posterior probabilities for classification, but what are appropriate priors? We've started investigating L1 regularization for those of you who know about that as an alternative subset selection, and that naturally provides priors. We've also developed a statistic for determining whether a spectrum is in the library or not. Right? Our library is not, it's large, but it's not comprehensive. And as I said, we've also been doing stuff in the thermal infrared. It will be nice. There are issues about, I've just modelled the background as a spline with 2 knots. It'd be nice to be able to automate that process, deciding on the number and locations of knots for particular applications. Okay, so let me move on to the second part of the talk, which is identification of material mixes in hyperspectral images without using a spectral library. As I said, building spectral libraries is a very time-consuming process. Currently, it's easy to measure training samples with a spectrometer, such as a PIMA, which is the size of a shoebox, which is more portable than with a hyperspectral camera. They are large, especially if it's an airborne or a microscope. Also, airborne spectra are distorted by the atmosphere. There are atmospheric correction algorithms, but they're not yet reliable enough to enable reliable matching of airborne and terrestrial spectra. But I'm actually going to show you something I've just done in the last few days, which suggests that all may not be lost. There's a lot of interest in identifying pure spectra in the scene. As I said, they're called Endmember, some people call it blind unmixing. But in the end, it will still require either a person or a machine to identify those Endmembers. And you see why the automation is important later on. Okay, so let me return to that linear mixture model. If you think about from the air, it's probably at the pixel level, it's mixing is now more likely to be additive rather than multiplicative, but it really doesn't make much difference. For simplicity, I'm going to assume that the background has been removed. So for pixel I have this linear combination of my Endmembers, where I've now changed my alphas to p's, I'll explain in a minute, but they're non-negative. Now both the p's and the e's are unknown. And again, we assume the areas have a common covariance matrix. So note the scale indeterminacy between the p's and the e's. So it's common to assume that the p's sum to 1. So that's why I put in p's as representing proportions. That's what's called the convex geometry model. Okay. So the implications of the convex geometry model. If there are m materials and there's no noise, then the data lie inside a simplex with m vertices in m-1 dimensional space. The pure materials lie at the vertices. So if m equals 3, the simplex is a triangle in a 2-dimensional subspace. If m equals 4, the simplex is a tetrahedron in a 3-dimensional subspace. Okay, let me show you, just to convey some ideas and concepts, a toy example. I've taken a triangle, okay, and I've generated 1,000 random points which are mixtures of the vertices. Okay, I've added a bit of noise to represent white noise to represent natural variation or inadequacy of the linear mixture model. Now, this vertex, I've allowed pure samples to be retained, but here I've said I'm not allowing any more than 80% of this pixel and anything more than 60% of that pixel to be found in the data. Okay, because I think actually this represents what happens in practice. Okay, here are two existing solutions widely used. One due to a former colleague of mine, Maurice Craig, is now commonly called the shrink wrap algorithm. So you assume you know the number of Endmembers, which is a question itself, and you work in some, well, let's say it's m, you work in some m-1 dimensional subspace, and his algorithm finds the simplex with the smallest hypervolume constrained to surround the data. Okay, that's the pink solution. Okay, and you can see the noise, this is the truth, the noise can force the solution quite a long way from the truth, from the 2 result. There's another one due to Michael Winter, which is sold commercially. It's called EndFinder. And it's a mirror image. It finds the largest hypervolume constrained to lie among the data points. And of course, its problem is it can't get out here. There's no way it can get out there. Okay. So we developed this ICE algorithm a few years ago. Unlike other Endmember finding algorithms, ICE accounts for noise in the data. It doesn't assume that for every material in the scene there's at least one pixel which consists only of that material. Okay, so here are some technical details. It's a fairly busy slide. It's carried now out in a space called minimum noise fraction space, which for those of you who don't know, I'll explain shortly. Well, or it's sometimes called noise adjusted principal component space. Basically, principal components looks for directions, linear combinations maximising variance. The MNF transform looks for directions maximising signal to noise ratio, and I'll show you an example shortly. It's analogous to canonical variance space that we use for the Spectral Assistant for dimensionality reduction and decorrelation, and actually uses spatial context to estimate what's called the noise covariance matrix. So in that space, if there are n spectra in an image and m materials in that image, you choose the P, I, J, and EJ to minimise the following things. So again, it's a sum of 2 things. Let me focus on them one at a time. This is just the least squares fit of the model. And it's not difficult to show. I've actually said it as an assignment for my students this week that the solution lies in the subspace spanned by the first m-1 principal components. And then when you project the data onto that subspace, any solution which totally surrounds the data gives you the minimum residual sum of squares, right? It doesn't matter whether your simplex is small or large. So the Craig solution is 1, but I could have a bigger triangle, okay, that would give you the same residual sum of squares. So I actually want to favour, what he's doing is favouring solutions that hug the data. So if we're going to make that assumption, right, then we want some measure of the size of the simplex to counteract the fact that there's all this indeterminacy. Now, these guys use the volume, but volume is a determinant that's computation expensive. I've used something cheaper, which is the sum of squares of distances between the vertices. Why that's useful is because this thing is quadratic in the EJs, and it's quadratic in the PIJs subject to these constraints. So you can actually solve this thing iteratively very quickly. Okay, and there's a weight parameter, a regularization parameter mu, and the closer mu is to 0, the larger the simplex is, and we find that mu equals 0.01 appears to work well in most real-world situations. So if we return to that toy example, these are the solutions I showed you previously. These are two ice solutions with two different parameters, of the real-world one and one that works probably better in this example. So you can see with the 0.01, this one's almost perfectly obtained. It's a bit short for these ones, but whether you take 0.001, this is a bit high, but it estimates these vertices quite well. Okay, so just for an example's sake, let me show you a simple example in biology. It's from a hyperspectral camera from a company in Boston called CRI. It's of a mouse lung with a tumour, which has been labelled with something called green fluorescent protein. The mouse was dead when this was done. This is one of the legs of the mouse. It's between 500 and 650 nanometers, so it's in the green and the red part of the spectrum. It's got almost 200,000 pixels. It's fluorescence rather than reflectance, and I've normalised out the brightness by dividing each spectrum by its mean. These are the MNF images of those 16 images, and you can see most of the information is in the first three MNFs. There's a bit in 4 and 5, and then essentially nothing else. So we're going to have a look at this in a different way, but if we ignored that, we said there are 3 MNF bands, and that suggests there are 4 Endmembers. Okay, just like with a triangle in 2-dimensional space, there are 3 vertices. With if there's 3-dimensional space here, you're assuming 4 vertices. So now what I'm going to do next is look at pairwise plots of these first 3 of the 196,000 points in there. So this is MNF band 1 against 2. You can see in crude terms something that's got 3 corners, but there's a 4th thing going on up there, a 5th thing going on up there, and then there's this outlier here. So these explain why you have some more dimensions in there, but the bulk of it is in the first 3. So again, for the purposes of exemplification, let's assume there are only 3 materials. This is the tetrahedron that ice will fit, okay, in those first 3 MNF bands, and I've coloured each of the edges with a different colour but the same colour in each band. So this dark blue, for instance, actually lies essentially behind the data cloud. Okay, and you'll also note how it doesn't chase that outlier, whereas the other 2 algorithms I showed you will. And you'll see it's also missed this 5th one, as I've only assumed 4. And the other thing to note is it's not constrained among the data points. So that vertex is not a data point. So once you've got those, you can actually invert the MNF transform to see what these things look like. Right. So this isn't these points, the estimated Endmembers are not real because they're in points in MNF space that are not real, so you reconstruct them. What we put next to them as a sanity check is the points in the data that are the best exemplars of that, in the sense they have the maximum proportion. And what typically happens is the first you have a maximum proportion of 1. That sort of forces things close, forces a few things, usually not always, to be 1. Okay, and then we order them in decreasing order of maximum proportion. As this goes down, these tend to look less like their estimated things. And once you've got that, you can actually work out what you can produce proportion maps or concentration maps of each of these. I won't go into this except to note that this one, there are just 14 pixels which have more than 0.5 of this. So this is some sort of outlier. It might have just been dust on the screen. This is the tumour, and it's useful to look at the residual sum of squares image from the fit, okay, and then to look at the worst fitting spectra. And these are the 2 worst fitting spectra based on the residual sum of squares. And this is this outlier, right, and that's the fit. So if you fitted 6, you'd probably find this. This is the second worst one. This didn't have very much quantization. I think it had 5 bits or 6 bits of quantization. So you can see the quantization error in here. Statistically, it's probably a bad fit, but in practice, it's okay. Okay, let me come to a remote sensing example, which I'm going to talk a little bit about. It'll be the last one. This is from the original hyperspectral scanner, AVARIS, put up by NASA in 1985. This data from 1997. Stands for Airborne Visible Infrared Imaging Spectrometer. It's of a place called Cooperite in Nevada. It's a mining site in Nevada. It's actually got 224 images, but for various reasons I've restricted to this, one of which is the water band's just totally saturated, and so NASA have just set them to 0, so I can't use them. Okay, so I've used 51 bands between just under 2,000 and just below 2,500. They're at 10 nanometer intervals rather than 2 or 4. There are 600 by 500 pixels. You'll see the variation, except I've divided by the mean. Without division by the mean to take out the brightness variation, they all look the same, okay, to the eye anyway. Okay, you actually get much more information about shape by dividing by the mean. Okay, these are what the first 25 principal components of those data look like. You see there's a lot of signal at the end, but even way down here, you've got signal. Whereas if you take the MNFs, it compresses them nicely, and things broadly are reducing in what we call signal quality down to about the 14th, okay, which suggests there may be 15 things in there. But there are two things. Some things actually may be highly mixed and are very hard to find. The other thing is you actually might be getting some slightly nonlinear mixing going on, right? There actually might be a dozen things in there, but because of the slight nonlinearities, you're seeing them expressed in some of these other MNF bands, okay? When we run ICE, we actually, I'm showing you the result of running ICE with 12 Endmembers, and you'll see the maximum proportions decreasing, and they get down to 0.56, and then they drop to 0.34. This might be real, but this estimate is not very realistic looking, okay? The problem is when it gets below a maximum proportion between about 0.5, 0.6, this is a long way from the data cloud. It's really hard to estimate. And what happens is the proportion map, essentially, there's nothing in there, right? So essentially, the ICE can find 11 things in there, okay? And what I've done the last few days, as I said, in the end, you actually, if you want to automate this, you actually need something to somebody either manually or a machine to automatically identify these things. So I started looking at this issue. I've actually seen, can I take the Spectral Assistant library, okay, and identify what those things are? Because by eye, I can tell you that's a white mica that we saw before, and this thing is a candite, right? It's got that doublet I told you about. That's got the single feature. You don't have the one further over because that's also where water expresses itself, and so that's just been zeroed, okay? So what I've done is I've resampled the Spectral Assistant SWIR library from 4 nanometers to 10 nanometers. Not just subsampling, I've actually I know what the shape, the approximate shape of the filter function is. It's a Gaussian shape. And I know the width. You can find that from the website. And I fed the best pure materials and mixes of 2 materials to each Endmember. The results are reasonable, allowing for noisier average spectra and limitations of atmospheric correction used. Oh, I should go back. You can see in a lot of these things as a feature here in common. This is actually as a result of the inadequacy of the atmospheric correction. We think this is residual carbon dioxide left after the fit. So I've actually removed the first few bands here to emit this region. Okay, so that's the first Endmember. Okay, that's in black. And you can see there's some funnies going on up here, but it's basically saying you're getting a good fit of a mineral called calcite. Okay, very nice fit. The more impure spectra need to be fitted as mixtures. So for instance, this number 10, if you take the best fit, it sort of is shifted with a halloysite. But if you take a mixture of kaolinite and phengite, it fits this quite nicely. There may be a third thing in there. You can see some little funnies there. But you can also see this and here. These spectra are noisier, and we've been training with a different instrument. And there's some things there that are probably not in our library. So there's number 4. It's trying to fit opal or opaline silica. And you can see it's not quite right. It's probably something else that's not in our library. Okay. Just to finish quickly, there have been some recent extensions of ICE last year. A couple of papers by Zera and Gato on a thing called SPICE, which stands for Sparsity Promoting ICE. They add an additional term. For those of you who know about L1 regularization, this is taken from that idea. And they take for each Endmember, they take a different weight times the sum of the proportions. If you took the same one and inverted the same one, you could take it outside, then you can invert the sum, and then the sum of the proportions for each end member is 1, so it doesn't do anything, so you use a different one. And we've programmed it up. It doesn't really work all that well, to be honest. It's highly dependent on the application. And another thing, which is very impressive, is called minimum volume constrained non-negative matrix factorization by Miao and Key. It extends ice in 2 ways. It replaces the regularization term, which is the sum of squares of distances between vertices, by the volume, which is very impressive, but I don't really think it's necessary. And they also, as well as constraining the weights to be non-negative, they constrain the spectra to be non-negative, but they perform it in the original space rather than M&F space, so they lose out by doing that. Okay, the future. In the last year, I started working with our remote sensing group in Perth. They do continental scale mapping, mainly for environmental applications, using 6-band Landsat data. It takes about 360 Landsat scenes to cover Australia, which is roughly the size of the continent of the United States, so it'd probably be something similar. And you get, the images need to be corrected for lighting variation. So this is actually a mosaic with 3 of those 6 bands of Australia that have been corrected. And you can still see some boundaries, the boundaries between some of the images. And in particular, you have problems where, for instance, there's been cloud cover on a particular pass, so they have to wait for a later pass and put something else in. But they need to be corrected in mosaic to ensure consistency in overlapping regions. As I said, there are going to be up to half a dozen hyperspectral satellites due to be launched over the next 6 years. The remote sensing group would like to be able to do hyperspectral continental scale mapping. We currently work with some HIMAP airborne images, which I couldn't, it was too big to fit in here. I'll just, if you bear with me, bring them up. I'll bring up a colour representation of that. Mosaicing. Okay. So this is an airborne system, and it basically flies up, turns around, flies back, and it flies up. So here are 9 flight lines, and they make sure there's an overlap. And that's what's going to happen with these hyperspectral satellites. There will be an overlap, but not in one direction, but in both directions. And that each of those is about 11,000 pixels long by 700 pixels wide. Okay, so that's the sort of data we work with. We need to obtain good estimates of the number of end members in each scene. So the idea is to do a first pass of ice in each subscene, okay, and get a good estimate of the number of end members. And then to constrain the next, to run ice again with the constraint that the proportions in the overlap regions are the same, okay. And I don't think that's hard to do, but you need good estimates to begin with of the number of end members in each scene. Okay, other research focus on greater automation, integration of the spectral system allows us to deal with problems where some end members are known and some are unknown. I didn't speak about this, but it's incorporation of baseline and scatter corrections into ICE because standard tests don't work because those things aren't fitted very well. And incorporation of other constraints into ICE, particularly spatial context. We could also do non-negativity, although I don't think it's a big issue really when you do it in M&S space. That's the end. I'm sorry if I've run a bit over time. Yes?
Do you have some ground truth for some of the mixing?
For the airborne?
Well, just what kind of minerals are present? Not in general, for any kind of data. What kind of...
Okay, well, for this data set, the Cuprite data set, there is some ground truth because people have actually gone out, geologists gone out and actually said this is what there is. Okay, so you can do that. And but there are very few sites around the world where there is ground truth. But there is a campaign on to develop a number of sites that people can use for testing purposes, whereas there is ground truth. Having said that, ground truth is only a very approximate thing, right? Because you say, I can find these rocks here, but if your pixel is 30 metres on the side, it's going to be a mixture of things, okay? And people on the ground are not going to be actually to actually map everything on the ground. They're just going to be able to take samples. So there's a whole issue of how you actually validate with that sort of incomplete information. But there will be, I think over the next 5 to 10 years, there will be an increasing number of sites that have that sort of validation, but there are very few at the moment.
Also at ICE, the kind of data you showed, it seems that all of the data points are evenly distributed in all of that space, more or less. So you don't have clusters there. Is this correct?
In the data that I've looked at, yeah, I don't think I've ever seen clusters. I've seen papers which work on data with clusters. And you could imagine in an agricultural scene that you might find that. But I've mostly been working with mineral scenes, but I'll be working more with environmental. And I suspect those are going to be highly mixed as well, particularly in an arid country like Australia, you know, where desert will be, I don't know what desert will probably be fairly boring, but quite easy. But in those sort of semi-arid zones where you have probably some sparse vegetation mixed with soil, you know, you're going to get mixtures of soil and vegetation. So I forgot what your question was. Oh, about having.
I'm just asking about it because it seems to me that if you do have clusters, that this algorithm would not work correctly of estimating the birds. It sort of works well when it looks like.
Possibly you're right. I don't know. As I said, I've not, in practical terms, I've not seen data that has separate clusters. But clearly, one could imagine that if you had, if there were clusters and you can visualize those clusters, it shouldn't be very difficult to separate them into separate clusters and then run that algorithm on the separate clusters. But as I said, it's not in my thinking because I've seen lots of data sets. I've actually never seen data that are clustered. In fact, there's a data set I give in my course that it's not quite that. It's glass beads on the background, and you expect those to be separate, classes, and they're mixed because the boundary pixels between the individual bead. There's 7 types of beads. The boundary pixels between the individual beads and the background are mixed, and you get a central bit with lines. I can show you if you're interested. It's a rather neat example. So it might be that would work then too, even without the separation of the clusters. But anyway, I mean, you could separate the clusters first if you needed to.
So you mentioned there are satellites coming up that have hyperspectral imaging capabilities. Are they all commercial satellites? Are they used for mining primarily? Or
they're all going to be fairly similar in terms of their wavelength range. You're all going to have about 200 bands between 400 and 2500 nanometers. How they're going to be, none of them is actually being launched by a commercial organisation. They're all going to be launched by government research organisations. So presumably that they will be reasonably freely available. But exactly, you might have to pay a certain amount to download a scene. But I don't think at this stage that they're going to be commercial satellites. I could be wrong, but I doubt it.
More questions?
Thank you.
Thanks, Mark.